My name is Sang Kim, MIT, running Biomedical Robotics Lab. Today's speaker is actually Youngman. I'm just trying the beginning part of the talk. So we're going to talk about humanoid control. Before talking about controller, I have to introduce a new platform we've been working on during the pandemic. We submitted a simple trajectory planning paper on back collecting. Those are actually realistic spec from the hardware I'm showing in the right. It's not walking or running yet, but everything's functional. I will show you a couple of philosophy on design and what we're trying to do with this platform. When we decided to do humanoid, we thought about why we're doing humanoid. We had to really think about the objective of study. So we found the ankle is heavily underutilized, and then we realized ankle actually play a huge role. If you look at human and animals, even quadruped animal, the legs are pretty much straight when you hit the ground. But none of our robots can do that because the impact is going to be huge. You can't really control the ground force. And only that's possible in the animal world. We have an extra joint, like a human, and we have an ankle. And the quadruped animal, they also have a little bit of ankle, but they also have a scapula. So that's okay to be straight. The reason why we care about straight leg is actually that allow you to have a bigger workspace. When we discuss about like the robot like a cheetah, some people ask like, why don't you have an ankle? Like, I love to have an ankle, but it's added complexity. So I'd rather have just a little bit longer leg and then not have an ankle. And yet, so it's actually okay for quadruped. Quadruped, I think I still rather keep no ankle and then simplistic design. But when it comes to biped, when you bend your leg a lot, not only you lose workspace, you also have a much higher collision chance because your both legs are bent. And then trying to avoid collision is much harder than when legs are straighter. So you lose a workspace in both ways, not only just like reachability, also you can really, if you think about like the dancers, they can do all kinds of movement because their legs are more straight. And then we heavily utilize our ankle. So if you study, like look at the biomechanical studies, like ankle does a lot of work. Even walking, actually the vast majority of mechanical work done by ankle. Even jumping, the ankle does the 20% of mechanical power. So we're trying to really use the ankle a lot more. That's one of the things we want to really achieve. And also, not only the functionality, also control aspect, the ankle does allow us to modulate the COP a lot better. Another aspect is the arm. There are a lot of robots that use arm to balance, tail to balance, and we would like to study how actually arm can actually improve our stability in the locomotion, particularly for biped. Charles already with the presentation on some simple case. We'd like to expand that to the more general locomotion case. Robots are designed to really large workspace, and you can really like sit down completely and then stand up, and then you can leg day all the way up and all the way down. And the total robot is about 22 kilograms. It's about 8-year-old height. The reason is we learned that from cheetah, when the robot is smaller, it's so much easier to experiment. And then exporting to the bigger machine is not a big deal. It's just the same thing. So we try to make it as small as possible. We have 8 degree freedom, 5 per leg, and then 4 per arm. And kick torque, knee is like 140 Newton meter, hip is 7 Newton meter, ankle 66. Knee is a little bit excessively high. This is also the caused by our philosophy. We want to try to walk like a more straight knee, even though we haven't done yet. So that if knees are pretty much straight, it's actually the reflective inertia, the motor inertia doesn't play that much. The legs, knees are already like very singular. So it's okay to put higher gear ratio on the knee so you can actually jump higher, we can stand up from the knee. So we actually have a pretty high torque knee. We've been working on many different approaches, and today we're only going to show the FTC part. We're also working on the machine learning and trying to find a good combination of it. So with that, I'll invite Youngman to really give a talk.
Hi, everyone. My name is Randy. I'm a postdoc at the Biomimetic Robotics Lab. Prior to joining the lab, I had the pleasure to work with Professor Park on quadruped locomotion. I spent the first 2 years developing a custom prototype robot where we designed a compound planetary gearbox, which can achieve 23:1 gear ratio within a compact space. Once we have assembled the quadruped platform, the first experiment that we did is a vertical jumping experiment where we use a QP-based controller to achieve a 0.65 centimeter high jump and land safely. Once we have the platform ready, I moved my focus to developing NPC controllers. As we know, if we use Euler angles to represent the orientation, then we might run into the issue of singularity. As shown in the figure, it's normally known as the Kimball lock. In order to tackle this problem, we propose a NPC controller that directly uses rotation matrix to represent the orientation. We linearize the dynamics around the current orientation ROP and use a variational vector delta R, which lives on the tangent plane around the current orientation. In doing so, we can circumvent the singularity problem where the robot can pass the pose where the pitch is 90 degrees up, which will normally throw out the Euler angle-based controller. And this controller can enable this behavior and land safely. My research focus has always been focused on achieving highly dynamic leg locomotions in challenging terrains. On the left-hand side, you can see I used a mixed integer convex program or MICP-based motion planning algorithms to plan for a motion where the single leg robot is able to come up with a strategy of utilizing the platform on the left-hand side to reach the goal. In order to improve the scalability of this problem, we combine the sampling-based method as well as the optimization-based method to come up with a 3-jump strategy. As you can notice in this video, the robot makes an additional jump on the left-hand side in order to reorient its momentum to reach the goal. Ever since I joined the lab last year, I've experienced a transition from quadruped robot to humanoid. And here I want to talk a little bit about the comparison of these two legless systems. For quadruped robot, the leg mass is quite small and it's negligible, and the torso dynamics dominates. And because the legs are so light, we can step very fast, which improves the stability of the locomotion. Another point that's not often mentioned is that quadruped robot has legs spread out pretty far away, so self-collision aren't usually considered explicitly. And in general, we are more generous for quadruped robot because even if the quadruped COM is relatively low, we will not have any issue with that. But if the humanoid has the same knee bending moment, then we're going to come up and ask about energy efficiency issues. So there are definitely additional hurdles for humanoid locomotion control, and one of the most important one is the leg mass is no longer negligible. So when the leg is swinging, the swinging effect is more significant. And as a result, humanoid can achieve much lower stepping frequencies, and that means that the step location choice becomes a much more important issue. In addition, since the humanoid has the legs pretty close by and the self-collision has a much higher probability, so we need to explicitly consider that. However, the silver lining is that since humanoid has much higher central mass height, the pendulum dynamics still dominate. That partially explains why linear inverted pendulum-based method was so successful in the past and is still useful at present. And last but not least, I don't know about you guys, I get much higher dopamine hit when the humanoid flow works. Here I present an overview of the controller. So we developed a linear model predictive control based locomotion controller tailored for MIT humanoid. The LMPC can reason about footstep location over the horizon while taking into consideration of the kinematic limit as well as the terrain. In addition, we can also reason about contact range, torso rotational dynamics, and the varying central mass height. The proposed framework is suitable for real-time application because the LMPC and overlay control can both be transcribed as quadratic programs. Our lab has a long history of success stories where we use a single rigid body model for quadruped locomotion. For the quadruped, the control input is the ground reaction force because we make point contact with the ground. For humanoid, here we propose a augmented single rigid body model where we have an additional variable C, which represents the current stance foot location. The humanoid also makes line contact with the ground, which means the control includes both the forces as well as the moment terms. In addition, we have an additional variable delta C, which represents the stepping strategy. In this video, we show the LMPC framework applied on MIT humanoid in simulation. Here, the MIT humanoid is trying to traverse a wave field, and the interesting observation is that when the robot is walking downhill, its gait is more gingerly, and while it's walking uphill, it's more brave. We do not know why. So here I present a discrete linear dynamics. We have an additional term highlighted in yellow. Here, the A and B matrices are the Jacobian matrices, and the A can be calculated by taking the partial derivative of the dynamics with respect to the state. Delta C here, as I mentioned before, is the stepping vector, and it's pre-multiplied by a matrix AC, which is nothing but the last three columns of matrix A. The matrix AC quantifies how taking a step is going to affect the dynamics. The whole system is linearized and relinearized at each time instances. And the stepping schedule is represented by a binary vector eta. Suppose eta k is equal to 0, then the linear dynamics reverts back to the single rigid body dynamics. However, if eta is equal to 1, that means at that instance, a step was to be taken. Please note that eta is not a decision variable, but a constant parameters passed to the MPC. To illustrate how eta evolves as time progresses, we can see in this animation. On the bottom, we can see the left and right stance schedule. Let's assume here for simplicity that the robot only makes single support phase. That means that the contact location instantaneously jumps as we take a step. If we choose the prediction horizon to be slightly longer than the stance time, then there could be either 1 or 2 stepping chances within the horizon. This is particularly nice for the following reason. When the robot is at the early stage of a stance and the swing leg has much higher freedom to choose where to stand, then even if the robot is pushed, you will have the capability to recover. However, as time marches forward and the robot reaches the later stage of the stance, the swing leg has much narrower window to change its stepping location. However, in this framework, MPC is aware that towards the very end of the prediction horizon, there will be another chance to take a second step. In doing so, the MPC is able to provide a much robust stepping strategy. One of the major advantages of a optimization-based stepping plan is that it can explicitly consider kinematic limits. Say if the robot is about to take a step, then we can impose inequality constraint on the length of the step. Here, because we can see either 1 or 2 steps into the future, the inequality constraint threshold is scaled by I. Note that the delta C is defined with respect to the current location. A second point is that we can prevent leg overextension by imposing inequality constraint as well. So our hardware team has done a great job in mass distribution to locate the central mass position near the hip joint. So if we define the vector R as the vector from the center of mass to the contact location, then we can impose the following inequality constraint. However, we do not need to impose this constraint at every time instances. We only need to impose when a step was planned to be taken. So we have an additional term, 1 minus eta times m. Here m is a large positive number. When eta is equal to 0, then this inequality constraint is not effective. However, if eta is equal to 1, then this inequality constraint is effective. Please keep in mind that this leg extension constraint is only enforced for a few time steps. That is because the linear MPC has poor prediction capability for the kinematic, so it's only valid for a very short horizon. On top of the model predictive control, we also impose the Humanoid controller, which takes care of the following 3 aspects. First, it leverages the foresight coming from the linear MPC by tracking the torso movement, the swing foot movement, as well as the ground reaction range. The second aspect is that it's able to exploit the full body dynamics. The third one is that it's able to respect the physical constraints. Here we present a simulation study where we compare the following three stepping strategies. The first one is the capture point without any kinematic limit. The second one is the capture point with some kinematic limit. And the third one is our stepping strategy. The MIT humanoid is pushed really hard in the forward direction and is trying to recover from the disturbance. So in the first case, because the capture point is way beyond the kinematic limit, the robot fails. In the second case, the capture point is kept at the maximum value. However, since the stepping strategy and the MPC are agnostic to each other, so we cannot maximize the efficacy of synergy. So this control strategy also fails. Our control method is able to recover from this motion because we can simultaneously reason about step location, center of mass motion, the torso rotation, center of mass height change, and contact branch together. So the previous videos are all implemented in MATLAB, and we have since been working on migrating the MATLAB code into C++, and we have some preliminary results here. So in this videos, only the MPC is applied and robot is stepping in place. There's no forward control yet, but it seems like it's working okay. So if you take a look at the lower left corner, we observe some interesting emergent behavior where as the disturbance force increases, the robot is able to figure out a leaning forward posture to counteract that. Okay, moving forward, we are definitely looking forward to implementing the locomotion controller on the MIT humanoid hardware. And we also looking forward to using central model instead of single rigid body model. And we also have interest in exploring the heel-to-toe walking, but this direction was put in our back burner, mainly because we don't think the current MIQP solvers are fast enough. However, during this ICRA, we found promising methods such as ADMM-based method from microclosed group or multicolor tree search. So we're definitely very optimistic. Finally, I'd like to thank my collaborators and PI, Professor Song King, for giving me the support and the freedom to do the research. And thank you for your attention. I'm happy to take questions.
Awesome. Questions, everyone? Please just indicate if you're asking Yanwen or Senpei. I may have a question for you, Yanwen, actually. So you mentioned in general in the beginning that for the quadruped, for the cheetah, for example, versus the humanoid, that the humanoid has a higher leg inertia, right? So it was okay using the centroid or single rigid body model for the cheetah, but you're also using a centroid as a single rigid body for the humanoid. So where is the leg inertia compensated for dynamically?
This is a very good question. I think in the presentation that I had now, the whole body control takes care of that. However, as we know, the whole body control is not that easy to tune, right? So definitely we need to consider that at much higher level. What I want to say is that this controller is tailored for MIT humanoid, and the hardware design team has dedicated a lot of effort in moving the motors upwards close to the torso. So we are closer to single rigid body model than other humanoid. However, we are definitely at the boundary where this assumption is breaking up. So we are definitely going to explore alternatives.
But truly, out of curiosity, do you think of something? Do you have a direction that you can compensate for that, still keeping the MPC linear or QP solvable, let's say?
Yes, so the first thing I want to do when I go back is to implement the central dynamics model instead of the single rigid body model.
Another way to compensate the leg inertia, which is actually 3D, it's actually counteracting with the arms. That's why one of the reasons we need to study on the arms. As a default, like the reaction is another thing, but the reference trajectory can already cancel majority of the moments in 3 axis.
Yeah, really nice work. Love it. crutchy. Is this related to your not using the ankle in the controller, or is that is it a controller-based problem, or you don't want to, you don't care about it? Because we observed that if we have this singularity using, we have like massive drop in power, so we have a really good cost of transport going human-like, and I guess you're still using a lot more power if you go crutchy. That's going to be costly, right?
It's definitely a very good question. We are, as a lab, at the very early age of humanoid locomotion control, and our priority is to make something work first. However, we acknowledge the efficiency of straight knee walking, but that means relinquishing some control authorities in terms of locomotion stability. So we are working towards that goal, but currently we're at the stage where we use the full leg contact without the heel-to-toe motion.
Literally baby step right now.
Thanks so much.
Hi, my question's for Sunday. A few years ago, I remember there was a paper from your group that compared the knee direction, which actually suggested that backward-facing knees were more efficient. And if you look at in nature, the fastest and most communicable bipeds also tend to have backward-facing knees. So I'm curious why, when you go around to making your own bipedal robot, you chose more human-like knees than cool dinosaur legs.
Very interesting question. This is actually very commonly raised among biomechanics. But if you look at almost every single animal, their first joint from the body is actually pointing forward. So you might think like the ostrich. How about ostrich? Ostrich's hidden joint is actually pointing forward. Human is obviously this way. Dogs, the front leg, the scapula actually is moving like 30 degrees back and forth. That's actually pointing forward as well. So without almost exception, all mammals and dinosaurs, their first joints are pointing forward. There's a dynamic reason for that. The paper we published a long time ago, that was actually studied in a way that like almost every possible combination of the geometry, topology, and the frequency. So the paper shows that the knee back was actually more efficient, but their step length was very, very small. So like very high frequency, very small step, that's the only way you can achieve high frequency. So it's very hard to generalize that way. But if you just thinking about the swing speed, for example, I think that we believe that first joint pointing forward is better.
Thank you for the great talk. I have a question about the design of the humanoid robot. I think it's a really clever idea to design humanoid robot to emulate the linear inverted pendulum so that we can simplify the design of algorithms instead of considering the heavy nonlinear high dimensional dynamics. We just consider the robot as a linear model in some scenarios. But I'm curious about your insight into any general guidelines for hardware design so that we can minimize nonlinear, because when the robot moves faster, the nonlinear effects will be more significant. For example, with speculative or running or transitional periods during fluid coloring. I wanted to hear your insights for any general guidelines for hardware design or algorithm.
So our design philosophy is always minimizing the limit so that you can have a high, I mean, if you look at your bodies, your muscles are always proximal part of your joint. My muscles that control my elbows are always upper, close to the body. We apply the same idea, like motors are always close to the body so that the lift can be fast. At the same time, when you lift to the ground, it's less of an impact because inertia is less. The price paid for that kind of photo, you have to have a lot of transmission belts or some cables, and that added complexity and the frictions and so on. So we have to find the right balance between that. If you do too much, you get too complex and it get very fragile. That's another thing. Like if you design a robot, where it falls and you have to fix for a couple hours, that's really not good for our research. So we are designing in a way that it can humble and so that just get back with no problem. So the robustness of an impact is also very highly regarded in our design. So yeah, simplicity and then minimum inertia of the life. It's basically the guiding principle.
Yeah, thank you. I have another question. So, what are your thoughts on the challenges and opportunities for lowering the price tag for humanoid robots? We've seen some success with quadruped robots, terms of having low cost, much cheaper hardware available for people who work on our systems.
Asking about prosthetics?
The price tag for humanoid robots.
Price,
Yeah.
I can't really guarantee, but this one, if you mass produce, I believe it can be less than $20,000.
Oh, that'd be good.
Yeah. But this is if there's a market.
Let's try to convince Unity to bring more cheaper humanoids. Sorry, man, we won't be able to take more questions. So maybe you can just ask them offline and post the sessions. Cool. All right. The last speaker, yeah, thank you.